Greetings from IIT Kanpur. Welcome back. We saw that there are lots of factors, especially the scaling and the requirement for packing devices and all pushed VLSI technology. At least that was the motivation. But then there may be motivation, but the environment and other factors may be needed for ensuring that that does happen. So today in this discussion, we will talk about enablers of VLSI technology. What are the key factors? I've divided into broad factors. What are the key factors that enabled it? First, the disclaimer. Then this is the outline of this topic. So I have divided it into these following categories, as I understand are the factors that allowed VLSI to really happen. First is, it was a wise choice of planar technology, the very approach of building chips, how to build circuits. And it's interesting that it still continues and it's likely to continue for many decades to come. What are the factors associated with materials and the development and advances that took place in that? Then the very fact of the processing, which involves various unit steps. What are the examples of processes? And more than examples, just to remind everyone that there is a whole range of technology that actually supports them in terms of processing, and similarly the ability to characterize the devices and chips and materials that you are using in VLSI. So without characterization, there's no possibility of achieving it. And then finally, some other supporting technologies which we sometimes may not even realize are strongly helping in ensuring VLSI technology is made possible. So let's start off with enablers of VLSI, the planar process. Let's look at it a little closely. The whole idea is that the chip, which is a 3D device, needs to be captured in a 2D layout. If you are able to do that, we are able to get circuit designers involved, and they can work in their own way with some design rules, all sorts of sophisticated and complicated circuits. And the process engineer will be able to ensure that given a circuit, they will be able to make the device work. So how to do that? That abstraction is important. The ability to separate out circuit design and processing, so that any circuit that comes can be processed. So that type of approach. So first, the circuit designer will conceive of a circuit. So here I have shown as a sample the CMOS inverter, where you have PMOS and NMOS, and there is an input and output. It behaves like an inverter. Now, what you eventually want is to make it into a device. Here I am showing the cross section, schematic cross section of what would be built. So you have a NMOS and a PMOS, and you have the gates and various types of materials that are needed according to the MOSFET. Now you need to transfer this to this. And supposing another designer comes and wants to make the PMOS larger or smaller, and similarly NMOS larger or smaller, or wants to make the metal lead somewhere else, you should have a process such that independent of what the circuit designer does, the process engineer will be able to build it and pass it back to the designers. So first thing is to be able to collapse this circuit diagram or expand it, whichever way you want to look at it. You want to capture what this circuit is trying to do for a given technology that is in which you are going to implement it in terms of a layout. So here what is being done is the different device aspects that are there. For example, the well of a device, the source and the drain, the definition of the gate, and so on, where the contacts are going to come. All that will be captured with the help of some layers which have to be used for a mask. So so in the process, where the well will come will be defined with the help of a mask, and the mask has to be designed by the circuit designer. So now, once this layout is available, this is just one layout. There could be various types of layouts depending on the designer and application and what they are trying to do. They will all be passed to the process engineer, and the process engineer should be able to build this particular circuit based on the information given in the layouts. He or she should be able to build that actual hardware on silicon, okay, on silicon wafers. Now, clearly there should be some hand holding and handshake between the process engineer and the circuit designer, so that depending on what they want to do, they have to be told how to put together this layout. And here there are various constraints that may be there. For example, the distance between the two wells should be some minimum distance. So the drain of the N MOSFET and the drain of the P MOSFET, there should be some minimum distance. So such rules will be given, or what should be the size of the gate, because depending on what the process designer is able to do, they will be telling what should be the layout rule. For example, if the gate's dimension minimum they are able to make it is say 0.18 micron, some technology that they are 0.18 micron. So the circuit designer, when they are putting together, the designers, when they are putting together this layout, they should make sure that the gate size is never less than 0.18. And similarly, they may have some rules. You cannot just make it 0.812 or something. There should be some rules on minimum resolution that is possible. So these will have to all be decided mutually by discussion between the circuit designer and the process engineer. Finally, of course, the process engineer can only promise what is possible. They may take up challenges, but there is a physical limit of what is possible given a particular state of technology. So based on that, the rules for laying out the various mask levels, which defines the various areas, for example, the active area of the transistor, or the N well, P well, the polysilicon gate, how to define it, and where the metals will run, where the contacts have to come, all the rules associated with it, how many contacts should be there in a given transistor to ensure that the yield is good, or what should be the spacing between the contacts. So all this will have to be codified and will be given to the circuit designer. Once that is passed on, the circuit designer has the freedom to do what he or she wants to do with that. They can actually design any circuit they want, and as long as they are working within the limits of the design rules, the process engineer should make sure that they are able to deliver what they have promised. That is, if the sheet resistance should be some value, they should ensure that the sheet resistance should be some value. If the transistor threshold has to be some value, it has to be that value. So these things will have to be figured out. So, but then the beauty of this whole planar processing is you are capturing this 3D in terms of two-dimensional features, and usually the features are the masks that are involved, which decides in what part of the wafer what is going to happen. And in fact, there's a lot of IP that is riding, intellectual property IP that is riding on the mask design and the circuit design. And no wonder there are so many jobs also available for circuit designers. So because once the process is fixed, based of that, lot more circuits can be designed, right? So now what is allowed is in the control of the process person. Of course, they will be pushed. They will always be challenged. Why don't you make it better? Why don't you make it better? And if a particular fab is unable to deliver that, people will try to go to another fab where that process engineer is able to deliver what is needed. So because of the competition, everybody wants to push the limit. But finally, once the technology is defined, the process engineer sets the rule, and based on that, the circuit designer will design. So this is the broad basics of the planar process. So as far as the process engineer is concerned, the vertical dimension, they have a lot of freedom. They can do what they want in the vertical direction. But horizontal directions, once it is defined, they have to make sure that what is promised is delivered, and the vertical dimension should be tuned so that the final device works the way it should. Okay, so this abstraction is what is the key, which has helped in VLSI to succeed. So with every technology, the ground rules will change, because the process engineer realizes he or she can make something smaller, or maybe dope higher, or maybe ensure that there is more uniformity. All these things will be in a superior technology will be understood. So based on that, the design rules will be made more and more relaxed as far as the circuit design is concerned. The circuit designer wants to pack as much as possible, but the device engineer will say don't, because of the design rules. So that's the planar technology's broad idea. So let's look at the planar processing and technology a little bit more carefully, some of the points. So planar technology helps to abstract the whole processing, the three-dimensional processing that is going to happen to build the three-dimensional device, so that the circuits can be implemented. They are able to make it into two-dimensional. Now what is and in fact, as far as the device is concerned, it's in a two-dimensional plane. That being said, people have always wanted to push for three-dimensional processing. The reason being, you can pack many more devices. So where one transistor is there, if you can put 10 transistors one on top of each other, clearly you will be able to have higher density of devices, right? So there is a constant push for three-dimensional approach. While there has been some move towards that, in fact, some of the latest devices are in some sense three-dimensional. There are stacked transistors coming where N MOSFET and P MOSFET are on top of each other. One of them is on top of the other. So, so the three-dimensional approach is coming, and now another three-dimensional aspect is coming is you are having multiple chips on top of each other. So, sometimes sections of the chip will be made thin enough so that you are able to pack multiple devices. So there are lots of three-dimensional approaches that are coming. As of now, except for some areas, memories and certain other places, three-dimensional is more in the research stage, and I'm sure in the coming years a lot more three-dimensional devices will be made. Certain aspects of three-dimensional are already here, but it will really take off in a few years. That being said, even the three-dimensional devices invariably are approached in a planar manner. Often what happens is you do the planar processing and then you integrate, except for a few exceptions. So you make two-dimensionals and add them up to get the three-dimensional effect. So that's what is normally done. So planar processing is going to be here at least for some more time as the basis of fabrication. So what is planar? As it says, is on a plane. The whole process is done on a plane of a wafer. Okay. So deposition or addition of a layer or addition of material or implantation of material is all done on a full plane. Of course, with photoresist and other things, you decide where in the plane it should go, and that's where the masks come in. So once the deposition is done, so you might do some lithography, and then you may try to etch it and remove it from where you don't want it. So this is the normal game. We'll go into a little bit more detail in this in the subsequent lectures, but essentially the process is on a plane. So whenever you are making VLSI devices, you make it on a full wafer on a planar surface, and the communication with the circuit design is on what is to be done on the plane. Okay. With 3D, some changes may come, but even there you break up the 3D into multiple planes and you assemble them. So for a given process in a plane, the vertical dimensions are fixed based on the processing. So the process engineer knows how thick should be the oxide. So the thickness of the oxide will not be in the mind of the circuit designer at all. The circuit designer will just say, give me this threshold voltage. So based on that, the process engineer will make sure that the oxide thickness will be of a particular value. Similarly, the depth of implant. These are things that the circuit designer doesn't worry about. But the process engineer does worry about that, learns about it, and fixes it for a particular technology. And whenever the masks come, the process is done on all the different masks with the same implantation or the flame oxide thickness growth or whatever the process that is being done, or whatever etching is to be done. These are all done. The vertical dimensions sort of fixed for a given process, and the only variation you will find will be in the lateral dimensions. So this is one of the features of the planar process. So typically a combination of deposition and etching is what is needed to build the device, and where to deposit, and once deposited, where to etch. These are defined by lithography. So note that the lithography or the defining of where it happens, that's where the chip designer's role comes in, and the chip layout engineer, often they are circuit designers themselves. They work, or if not, they will work with core circuit designers, and they will do the layout. So they'll transform that circuit that we have conceptualized onto a layout. That layout will be given to the process engineer, and the mask essentially captures what gets deposited, what gets etched. Okay, so that is the core of planar processes. Now, I want to bring in one very important concept which sometimes we miss, especially in the traditional VLSI world, and increasingly in the newer VLSI world, these boundaries may get blurred. In planar process, we do all the processing in the horizontal direction, right? But what is interesting is the dimension that we normally consider, the order of magnitude of dimension we all normally consider in the planar dimension versus in the vertical dimension are often different orders of magnitude. The planar dimension that we have is typically way larger than the vertical dimension. To give a simple example, the oxide thickness may be, say, let me take an older technology, maybe say 50 nanometers. But the horizontal dimensions can be in the order of microns, or maybe 300 nanometers or 350 nanometers or some 500 nanometers. So the horizontal dimensions often is orders of magnitude more than the vertical dimension. This is a feature that you have to note, and traditionally they are more than 2 orders different. Okay, so if you look at it, when we are scaling things, notice that we are scaling the horizontal, the planar dimensions. But when you are building the device in 3D, and if you want it to be having proper aspect ratios, the vertical dimensions also have to shrink. So what has happened traditionally is the vertical dimensions have reached atomic levels much earlier, and so that scaling has decreased. On the other hand, horizontal scaling has continued, as we saw in Moore's law and so on. So what has happened is, over time, horizontal dimension, vertical dimensions are ending up coming close to each other. So schematically, I have shown there is a device. I have shown, of course, a cross section. This is a 3-dimensional, the Z plane, or the perpendicular to the plane of the screen. You have the rest of the device, which will change as you go for. So once the device is over, you will have isolation and so on. So once it is scaled, what you do is you make the horizontal dimension small, but it is expected that the vertical dimension also should decrease. You would expect that, right? Otherwise, you will find that the aspect ratios become very huge. If the vertical dimensions is remaining the same, and so we want the similar aspect ratios so that the properties of the devices remain same. Of course, doping and various other factors also come in, the nature of the material, the properties of the material used, all that comes into play. But typically, you want, when you scale it, you expect that the whole thing shrinks. To give an idea, supposing I'm wanting to shrink, you have a truck and you want to build a toy truck. Clearly, when you build a toy truck, all the parts of the larger truck will become small, correct? But sometimes, and ideally it should be totally proportional, right? But in reality, it may not always be that proportional, but first order, it should be proportional, but it should be proportional. But increasingly what is happening is, the dimensions are running into each other thanks to the physical limits and the atomic limits of the dimensions. So with time, horizontal sizes are approaching the vertical dimensions today. There is another reason I want to bring this up also. When we draw schematic cross sections, notice that the way I have drawn, this distance may be of the order of what I am showing with the cursor, maybe of the order of a micron or something. On the other hand, the vertical dimension may be only about tens of nanometer, 100 nanometers. But the way I have drawn it, it appears as though they are of the same order of magnitude. So typically, all cross sections that we draw, you have to keep in mind that the vertical dimensions usually are much smaller than the horizontal dimension. But in order to visualize it better, you of course change the scale and you want to highlight what you are building. So now, based on with this backing of basic information, let us see how an integrated circuit is built. My attempt would be to show the various blocks, building blocks that are there, and based on, and of course I'll try to keep processing at the center of it, because that's a focus of this particular course. So typically, when there is a problem identified, the circuit designers will start working on it and try to build a circuit. Maybe they want to amplify a signal, or there are some digital signals coming, they want to see if some particular pattern comes in, so they'll have to build a comparator and things like that. So they'll come up with a system, and of course systems can become more and more, have become more and more sophisticated over time, right? So once a problem is identified and you know what you can do, so you try to build a circuit with that. And from the diagram of the circuit, you go for a IC layout. We already saw that. That is one of the reasons why we are able to actually seamlessly able to shrink and do stuff and build a variety of circuits. So these are for problem areas. First block is circuit design, then IC layout. Following that, it will go from the IC layout. Once it is done, the masks will be then built, and then it will be sent to the processing unit. The processing block folks will end up building the thing on a silicon wafer. And then finally, once it is done, they'll cut it up, put it in a die, put it in a package, and then they would send it out as an IC. Once the IC is built, it has to go to IC verification, because just because it is built, you of course verify. Honestly speaking, in all this, a lot of verification is taking place even within each block. But this is overall verification of what is being what was designed as a circuit, and then it was after processing goes to IC verification. The errors can come because of two reasons. One, because of the circuit errors, the design of the circuit could have errors, or similarly, or the processing could be not up to the mark. So this IC verification folks will try to determine that. Of course, they'll first find out, flag what are the errors that are coming, and try to sort out what is the source of the error. Once that is okay, they'll incorporate the IC in a system. They build a more complicated system. Maybe they'll build a motherboard, and then they'll build a computer, or there may be a communication router or something. Then finally, the problem solution will be emerge by implementing it. So clearly, there are lots of feedbacks, as I mentioned, but there are two feedbacks that we would like to look at in this particular case in the context of processing. First feedback is that you have design rules. I did mention this earlier. So this design rule is the feedback, that is IC design person may design something and give initial stages, they may try it out, it may not work. So the design, of course, the attempt of the process person would be to relax the processing stress, whereas the circuit person will want to pack more and more circuits so that their circuits become more sophisticated. So it's always a tussle here, but usually the design rule is put together in consultation by the processing person who will pass this design rule to the IC layout person. So this is important, and based on the design rules, IC layout person will pass the masks with which the IC would be built. Then also you would have, when the IC verification happens, first person they will catch is the process person to say, has the processing been done correctly? Go and check. So they will give feedback. There is an error. The threshold voltage is not coming what it is supposed to come. Go and check where the problem is, and so on. And sometimes they may find that the oscillator is not working. Why is the oscillator not working? It could be a processing problem, it could be a circuit problem. Somebody might have connected the line incorrectly or whatever. So there is a feedback here. Of course, there is a feedback from here to IC layout person itself, you can say, but usually it also involves a processing person as far as whether the defect if it has come from the processing block. So there is this feedback. But with these feedback, that over time, what ends up happening is this forward path just goes smoothly. But there could be a local feedback like this, and as I said, there are lots of other feedbacks that also are there. Simulators are used to check the IC layouts, and that goes back to the circuit designer to see whether something can be adjusted so that you can ensure that when you put it on silicon, it will work. And similarly, within the IC fabrication, there are hordes of internal feedback. Every process steps, invariably you check it to see that you are doing correct, and there are a lot of statistics involved, how to check it and so on. So this is how the whole process is done, and clearly, at least I have portrayed it that way, and I do think it's a key block that is needed to make the concept of a circuit and the problem you are trying to solve into a reality in the form of an IC to find a solution. So all feedbacks, of course, are not shown here. Now, the takeaway on planar process. So, I would like to tell what are the takeaways for this part of the enabler of VLSI. Layout of circuits are created by circuit engineers, and then device, so circuit is built on, from with that the layout is made, the layout is passed to the process engineers, and then they go ahead and build the device. And this is possible because of the planar process which is adopted. So, that sort of collapses the 3D into a 2D, which is used for communication between the circuit designer and the process engineer. The vertical dimensions typically are much smaller in the planar process. This has to be kept in mind, especially when one comes up with new ideas. One may say that we'll do this and do that. We have to keep in mind what the actual dimensions are, and for convenience, as I said, they may not be in the same scale, the vertical dimension and the planar dimension. And with technological progress, we are increasingly seeing though that horizontal dimensions are coming closer to the vertical dimensions. Vertical dimensions have already reached close to atomic levels, maybe tens of atoms or hundreds of atoms, and today even the horizontal dimensions are coming close. For example, when we look at some of the transistors that are being targeted now, 2 nanometers that gate length. So, if you look at it, if it was physically 2 nanometers would be maybe around 20 atoms or so, right. If you take a hydrogen atom, the size is about 0.5 angstrom. So, one angstrom would be two atoms. So, if you say 1 nanometer, which is 10 angstrom, so 20 to 40, so that is the order. So, we are within hundreds of atoms we have come in some of the critical dimension areas. So, that means that we are coming close to the atomic limit, and that is something that we should keep in mind. Then processing block helps define the design rule. So, they finally have the veto power, because if you are unable to do it, you cannot take a design and try to fabricate and waste resources, right. So, you have to tell very clearly, if you give me within these dimensions and all that, I will be able to fabricate and your device will work. And of course, it is a responsibility, once that is commitment goes, it is a responsibility of the process engineers to make sure that that happens. And then once the process IC is out, the verification folks will give feedback and try to make sure that this will work. So, we will now go to the next enabler of VLSI. I would like to highlight what are the key aspects of materials and what role it plays, or it has played and continues to play in the development of the VLSI technology. So, of course, when you say materials, you can start with elements. So, this is a periodic table, I took it from the web. So, if you look at it, hordes of elements are there. Which is the element we should select? Which are the compounds based on those elements that we should select? And what are the materials we should make out of those elements? Okay, it can be in gas form and all that. Finally, we have to make it into a materials form, and usually we try to make thin films. That is the usual thing because of the planar processing. What is interesting is among all the elements, silicon has been the mainstay of VLSI industry. In fact, many people even call it silicon processing or silicon technology, although remember there are many other elements that are playing crucial role, but the base is invariably silicon, and that too silicon in the form of a crystal. Silicon has some amazing properties, and which is why it is good. It has really been selected. Now, that being said, we should remember there are hordes of other semiconductors which are also there. Germanium is another example. Today, carbon is also playing a role. I have not indicated it here in organic semiconductors. Carbon based materials can also be used, graphene and so on. And now, there is another thing that one can do based on chemistry and the fact that you can silicon, germanium, carbon, these are group 4, right. Now, you can actually combine group 3 and group 5, and if you are able to combine them, you again get another wonderful semiconductor like gallium arsenide, gallium nitride. So, there are various types of things, and not just that, you can mix and match. Gallium arsenide can become gallium aluminum arsenide and so on. So, there is a veritable zoo in a sense, so many semiconductors that are available, but out of all this, it is silicon that has stood the test of time. It continues to play an important role. Part of the reason I am just highlighting here are two other elements which are able to dope them very nicely. Of course, with time, besides boron, people have also used indium to dope silicon and all that. And then, of course, besides phosphorus, arsenic and antimony have also been used to dope silicon. So, but then the doping is an important aspect of a semiconductor, and which is why we are able to build the devices that we are wanting to build, like PN junctions and MOSFETs and so on, because the doping plays a very crucial role there. So, this doping for silicon also is available in nature. So, it seems as though silicon has played a very crucial role in the to make VLSI happen. So, it almost seems as though nature herself decided that she will make silicon so that we are able to make VLSI. Of course, I am telling it in a lighter manner, but clearly silicon seems to have all the properties that you would want in a semiconductor. The band gap is just appropriate, so that the leakage currents are not much, especially at room temperatures at which we normally have most of the electronics operating, and so on. Of course, there are some situations where you go to higher temperatures, then you have to go to some other other compounds like gallium nitride or something, or maybe even silicon carbide, a modification of silicon, right? So, but then typically for mainstay VLSI, it appears as though silicon was having all the perfect properties that you would wish for. You are able to dope it very conveniently with N and P, and various techniques have been developed. We will be looking at some of them in the course of this, as we will go further in this course. Remember that instead of silicon, the original devices were actually made in germanium. First transistors BJTs were made in germanium and so on, but germanium had its own challenges. It was more leaky and all that, and very soon they realized instead of germanium, silicon would be better, and once it came in, it has just stayed there. Other semiconductors also play a role, and they have some very niche applications. For example, you have, while silicon is one of the, it has been the mainstay for traditional VLSI, I must also mention that there are other semiconductors which have played a very important role, BiCMOS circuits and so on, and many other cases. Examples are gallium arsenide, gallium nitride, and as I said, high voltage circuits. For all these, you have various other types of semiconductors that are often used. And nowadays, of course, even organic materials are also starting to have some niche applications in semiconductor fabrication technology. But silicon's role is not just because of the semiconductor's properties alone. It turns out that silicon had one of the best interfaces with its native oxide, the Si-SiO2 interface. And this is what enabled MOSFETs to be actually of practical use, because the number of interface states are highly satiated, and as a result you can get controllable threshold voltages, and not just that, you can also have good mobility, reasonable mobilities because of the transport of the carriers at the channel. So the Si-SiO2 interface is actually a magic interface in a sense, which has allowed the building of good MOSFETs, and with predictable interface properties and the ability to satiate the dangling bonds. And also another important point is the thermal stress that is there, because during semiconductor processing you often have to take the whole wafer and the parts that have been built or in the process of being built to high temperatures and bring them back. The silicon dioxide interface actually is a wonderful interface where the thermal stress is very minimal. In fact, it's like a bomb. Whenever you do a process and things, you are exposing it to ions and there are defects and so on, very often you make a SiO2 grow there, and then you remove the SiO2. So then you have a pristine surface, which you can, almost pristine like surface, which you can now use for further processing. So SiO2 is a magic combination which has really helped. Besides that, silicon nitride, which is another compound of silicon, which also has very nice properties. Silicon nitride has excellent properties, which is used for various VLSI processing. It is a very good sealant, and especially it prevents diffusion of elements through it and so on. And polysilicon also, which is another form of silicon. Instead of the crystalline silicon, you make polysilicon by thermal deposition and various other processes, PECVD, CVD processes. So polysilicon also has a lot of good properties. And in fact, in the VLSI technology, eventually from the metal gates they move to polysilicon gates, and polysilicon also can be doped, and so, and since you can the N MOSFET and P MOSFET can be made very symmetric. So this leads to perfect self alignment, and this is what allowed for progression of technology towards smaller and smaller dimensions. Traditionally, so these have been the king, and silicon, although traditionally there's no question it was superior, today some cracks are appearing in terms of in the progress. People are wanting to substitute other materials. Some materials have already started making a headway in terms of in the oxides, hafnium oxide and some others are also being used. So you'll find that while this change has been happening, still somehow silicon clings on, and you find that silicon is the default option. You start with silicon, and if simply you cannot use it, you end up using something else. And not just that, the technology has advanced so far that even for high speed, what used to be high speed earlier, today silicon is able to handle. Of course, now we go to even higher speeds, so for that we may use some substitutes, but silicon continues to be one of the main materials for VLSI. It's not just silicon's role. Silicon, of course, has a prime role in making this, but there are various other materials aspects which are also important. First of all, with time, we get unbelievably high pure materials for VLSI processing. Parts per million for many materials, and sometimes even parts per billion purity is expected. In fact, if you are growing a wafer of silicon, the impurity levels, if you are willing to pay the price, of course, can be very, very low, parts per billion and so on. And not just that, the number of defects that appear in the crystal structure, for example, are also reduced. So the low defect and contamination materials in wafers, mind-blowingly sophisticated. And besides that, various gases and solvents also that are used for processing, they also have excellent properties, excellent purity. So this advances in materials is one of the reasons we can assure that what we are doing will happen. It's not some foreign element that is coming and sitting there, but the actual material that you want is going there. Besides this, the whole area of material science and technology has been progressing, and there is mastery over a variety of new materials. Although it must be said that silicon is one of the most studied material, and you have a lot of information about silicon, but that being said, it's not as though the other materials are not studied. So you find that a lot of other progress has been made. So there are a variety of materials that become available. Often we again bank on silicon or its modification. For example, you use silicon on insulator. That gave a big boost in terms of speed of performance and power dissipation factors at one stage during the VLSI advancement. So silicon on insulator, and then sometimes you combine with silicon germanium, so as to provide the stress and the strain that you need in the particular device. By playing with silicon and silicon germanium, you can achieve all that. Besides that, of course, other compounds, semiconductors, gallium arsenide and so on, nowadays are making, especially in hybrid devices. Then metals. Traditionally, aluminum was the favorite metal, because it used to flow very nicely, easy to handle and so on. But there came a problem with aluminum in terms of resistivity becoming larger and also electromigration. So copper technology burst into the scene. Besides that, tungsten has always played a role. Cobalt and nickel and various materials have silicides that can be used, and that ends up making the sheet resistance very low, especially for the contacts. So these things, they have played a very important role, the various metals that are there. And then also insulators. So of course, in electronics you have metals, semiconductors, and insulators, right? So insulators also we have now of course SiO2 is the magic material with a very high, very good insulating properties, but you can get even better ones. Of course, some of the advantages of SiO2 will go away, but you can, if where required, you can bring them in. High K materials, hafnium oxide is already part of the technology. Then similarly, you need low K dielectrics as well, especially between the interface where you want isolation of devices. You want very low K material, because the capacitance coupling should be as low as possible. So there is also a lot of work has gone on, and this dot 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 actually hides a lot more than what is revealed here. There are a whole bunch of materials, repositories available, and you can always use it as and when required. And whenever the VLSI technology requires something, people go back and look at that repository, and then they choose what they want, and then of course they try to use it so that the march of VLSI continues. So what are the takeaways in terms of materials which have enabled VLSI? Silicon somehow is a wonder material, and it was one of those rare cases where we hit upon the right material at the right time, and then VLSI technology took off, especially with MOSFETs. So material is extensively studied. Its compound, especially the oxide of it, silicon dioxide, those are very important combinations. And silicon dioxide by itself plays a very important role in VLSI. Silicon nitride and various variations of it have played a role. Silicon's polysilicon and its various forms have played a role. Materials with high purity is available and lesser defects. This is really playing a very important role in this progress of VLSI. And of course, repository of materials and available on demand, that plays a role. And this is made possible due to advances in material science and technology, which has played a very important role in the success of VLSI.